Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on these topics or are learning them for the first time, you're in the right place. Today we're continuing with functions and limits, looking at non-trivial limits of functions. So if you're ready to learn, then let's get into it. The concept of limits becomes especially important when we encounter combinations such as 0 divided by 0, which we saw with the sinc(x) function, or infinity divided by infinity, infinity times by 0, or infinity minus infinity. Of course, for combinations such as infinity divided by 0, that's obviously infinity. Infinity plus infinity is obviously infinity as well. And then 0 divided by infinity is definitely 0. And then for the finite cases, 0 divided by a finite number is 0, and finite divided by 0 is an infinite number. So these cases on the screen are the examples where we need to be careful. And I'll go through each of these now. So for the type 0 divided by 0, we can use something called L'Hopital's rule. And a proof of where this rule comes from we'll see in a later section of this course. But for now, we can just take the result. So for the limit, as x tends to a value x0, for two functions, f of x divided by g of x, if both f of x0 and g of x0 both equal 0, so both equal 0, then we'd have this function equaling 0 divided by 0. So the rule is that limit as x tends to x0 of f of x divided by g of x equals the limit as x tends to x0 of f prime of x divided by g prime of x, where f prime equals df by dx. So that's what the prime represents. And if unfortunately our f prime of x0 and g prime of x0 both equal 0 and we have 0 divided by 0 in the limit x tends to x0, then we just differentiate again. So we'll just have it equaling the limit of f double prime x over g double prime x. And if that equals 0, you do it again and you just keep going until we have a non-0 divided by 0 combination. Now let's look at a couple of examples of this. So for the type 0 divided by 0, before we used our sinc function, so let's look at that first. We did the geometric proof, and now we can look at it with a more substantial proof. So in the limit as x tends to 0 of sine x divided by x, what is that going to result in? Well, we know it's the same as differentiating sine x divided by differentiating x. So we have the limit as x tends to 0 of cos x divided by 1, as that's sine x prime and x prime become cos x and 1. And we know the limit of cos x as x tends to 0 is 1, and that's what we found from the geometric proof. So this is a better way of proving it using L'Hopital's rule. And another example could be this function. So in the limit as x tends to 1 of x cubed minus x squared plus 2x minus 2, all divided by x cubed plus x squared minus 2. This is again a 0 divided by 0 limit, so as x tends to 1, we have 1 minus 1 plus 2 minus 2. So those cancel and those cancel, so we have 0 on top. And then on the bottom we have 1 plus 1 minus 2, which is again 0. So we can differentiate using L'Hopital's rule, and we get the limit as x tends to 1 of 3x squared minus 2x plus 2 divided by 3x squared plus 2x, and that is going to be 3/5. So those are our results using L'Hopital's rule for the sinc function and this function here. Or another way that's equally valid for proving this second function is to substitute in x equaling 1 plus h, so that our limit is as h tends to 0. So to clarify that, this will become the limit as h tends to 0, where we've taken x to equal 1 plus h, of the function 1 plus h cubed minus 1 plus h squared plus 2 times 1 plus h minus 2, all divided by 1 plus h cubed plus 1 plus h squared minus 2. And I'll let you do this as an exercise, work this all through, and you'll find that, again, we get the result 3/5. So this shows that our L'Hopital's rule is also working, again, by using a different rule of an expansion where x equals 1 plus h. If we now consider the type infinity divided by infinity, we can't generally always use L'Hopital's rule, so a better rule to use is what I'm about to show you. So if we look at this function as in the limit x tends to infinity of 2x to the 5 plus 2x squared minus 1, all divided by x to the 5 minus x cubed plus 1, we can see that's going to be infinity divided by infinity, but this is undefined at the moment. So the way we can work it out is by factoring the dominant powers on the numerator and the denominator. So in this case they're the same. We can do x to the 5 on top, x to the 5 on the bottom, and we'd have 2 plus 2 over x cubed minus 1 over x to the 5, all divided by 1 minus 1 over x squared plus 1 over x to the 5. And we can then cancel out these powers of x to the 5 here, and then these fractions, as x tends to infinity, they'll all tend to 0. So we're left with just 2 divided by 1. So our answer is 2. And we should have expected this finite answer because the dominant powers on the top and the bottom are the same. Whereas if we look at a case where they're not the same, as in limit of x tends to infinity of x to the 7 plus 6 divided by x to the 6 minus 5, we'll get, if we factor out the smallest dominant power from either the top or the bottom, we'll get the limit as x tends to infinity. So for this case it's the bottom that has the smaller dominant power, so x to the 6, 1 minus 5 over x to the 6, and on top, if we do the same, x to the 6, x plus 6 over x to the 6, we can see, again, these go to 0, these x to the 6's cancel out, and we're left with the limit as x tends to infinity of x divided by 1, so just x. And so that is going to equal infinity, or it's going to be an infinite number. And in the opposite case, if we looked at something where the denominator is larger, so x to the 4 over x to the 8, and we have these other terms, minus 3 and plus 2, then the same thing will happen, but in reverse, and we'll have a 1 over x to the 4 here, and so, sorry, this should be x tending to infinity, so as that tends to infinity, we'll have it equaling 0. So for the type infinity times 0, there was quite a lot of writing for this example, so I decided to write it out first and I'll talk you through it. So for this function, we have the limit as x tends to infinity of x to the half times by the square brackets, including x plus 1 to the half minus x minus 1 to the half. And clearly here, this is going to be our infinity, and then this square brackets will be our 0, because as x gets larger, as it's tending towards infinity, these 1s will become less important, and it will basically be x minus x, or root x minus x, and that will be our 0. So we've got infinity times 0. So the first step is to take out a square root of x from both of these brackets, and they'd be here, and then we can take it out into the outside of the square bracket. So for this first one, we'll just get the power of half means it will be x divided by x, so 1, and then 1 divided by x, so 1 over x. And the same here, but with a minus sign. And then the next step, we can binomially expand. So do a binomial expansion of both of these brackets, and we get 1 plus 1 over 2x, and x squared and x cubed terms, and the same here, but with minus signs everywhere. And then when we sum these two brackets together, we'll have our x on the outside as it was here, and then these 1's will cancel, the 1 over 2x will add to the 1 over 2x, and we'll get 1 over x, and then these 1 over 8x squareds will cancel, and then the 16x cubes will sum together, and so now you're caught up. This will become the limit as x tends to infinity. If we times the x by our bracket inside, we have 1 plus order 1 over x squared. And clearly, as x tends to infinity, this 1 over x squared order, it doesn't matter what the constant term is on top. So here, the constant term on top would be an eighth. But as that tends to infinity, the whole thing will tend to 0, so we just have 1 as our answer. So again, for this case of infinity minus infinity, I've decided to write it out first, and I'll talk you through it. So as x tends to infinity for this function, we have this term being infinite and this one as well, so we have infinity minus infinity. The first thing we need to do is take a factor of x out of both of these brackets. So for this bracket, it will become 1 over 2x squared with an x here, but then we can times it by that x and factorize out this x squared. And then the same thing can happen here. There'll be an x here, times by that x, and we get our x squared. So this becomes 1 over 3x squared. And if you notice, this line here is actually infinity times 0. So the x squared is our infinity, and then this whole part here is going to be the 0. This term, as x tends to infinity, will go to 0, and so will this one. So we just have 1 minus 1, and then infinity here. So we have our infinity times 0. So all we need to do is the same steps as above, where we binomially expand and then work out our answer. So as you can see, I've binomially expanded these two brackets, and we get these terms here. And then when you sum these terms, the 1's will cancel out. The 1 over x squared plus 3 over 2x squared becomes 5 over 2x squared. Then the terms after here will be x to the 4 and so on. So this is order x to the 4. And then if we can times our x squared in here, we'll get the limit as x tends to infinity of 5 over 2 plus order 1 over x squared. And obviously, as our x tends to infinity, this 1 over x squared will become 0. So our answer is 5 divided by 2. So I thought I'd add in this extra case of 1 to the power of infinity, as you might expect it to be just 1, as 1 to the power of anything is 1. However, we'll see that isn't the case. So for this function, as x tends to 0, this 1 minus x will just become 1, and then the 1 over x will become infinity, so it will be 1 to the power of infinity. From here, the first thing we need to do is take logarithms. The limit as x tends to 0 of 1 over x ln 1 minus x. And we can now work out this limit and then undo the logarithm to work out this limit. So for this limit here, we have the 0 divided by 0 rule, as this part is 0, as x tends to 0, this is ln of 1, and then this is obviously 1 over 0. So what do we do in this 0 divided by 0 case? We use L'Hopital's rule. So we can differentiate, and we'll get the limit as x tends to 0 of minus 1 over 1 minus x is the differential of ln 1 minus x, all divided by 1, because 1 over x is just going to become the 1 over 1. And then this will become just minus 1. As x tends to 0, we're just going to have minus 1 over 1. And so as we've worked out the logarithmic case, we can then undo this, and we can see that this will actually be e to the minus 1. Today, we've learnt about the non-trivial limits of functions. This draws an end to the functions and limits section of the functions topic. In the next section, we'll be looking at differentiation. So if you want to learn more, I'll see you there. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.